Hello, students. Welcome back to class. Today, we'll be diving into simple AC circuits, part 2. But before we begin, let's take a quick recap of what we covered in our previous lesson. In our last class, we learned some important concepts about alternating current. First, we explored the nomenclature in AC circuits. AC is special because it keeps reversing its direction at regular intervals. Next, we looked at peak values and RMS values. The peak value is the maximum current or voltage reached during one complete cycle of the AC waveform. The RMS value is a way of expressing the effective value of that alternating current or voltage. And finally, we studied inductive reactance. This is the opposition an inductor gives to the flow of alternating current in a circuit. In our lesson objectives today, we will focus on two key concepts. First, we will discuss capacitive reactance. Next, we will study impedance. Now, let's look at capacitive reactance. Capacitive reactance is the opposition that a capacitor gives to the flow of alternating current. It is measured in ohms. This opposition happens because a capacitor charges and discharges as the AC changes direction. This process delays the current flow and makes it harder for the current to pass through quickly. The formula for capacitive reactance is capacitive reactance equals 1 divided by 2 times pi, times the frequency, times the capacitance, where F is the frequency of the AC, measured in Hertz. C is the capacitance of the capacitor, measured in farads. And XC is the capacitive reactance, measured in ohms. Here's a real-life connection. Capacitive reactance is very important in devices like radios, televisions, and power supply circuits, where capacitors are used to control signals, filter noise, or stabilize voltage. Let's solve this example step by step. We are given a capacitor of 5 microfarads, connected across an alternating current supply of 200 volts RMS, at a frequency of 50 Hz. We are asked to calculate 1. The capacitive reactance, 2. The RMS current, and 3. The peak current. Step 1. Finding the capacitive reactance. The formula is capacitive reactance equals 1 divided by 2 times pi, times the frequency, times the capacitance. Now substitute the values, 1 divided by 2 times pi, times 50, times 5 microfarads. Remember, 5 microfarads means 5 times 10 to the power of minus 6 farads. So we calculate, Xc equals 1 divided by 2 times pi, times 50, times 5 times 10 to the power of minus 6. This gives approximately 636.6 ohms. Step 2. Finding the RMS current. The formula is RMS current equals RMS volt divided by Xc. So we take 200 volts, divided by 636.6 ohms. This gives approximately 0.314 amperes. Step 3. Finding the peak current. The formula is peak current equals root 2 multiplied by RMS current. Root 2 is approximately 1.414. So, 1.414 multiplied by 0.314 gives approximately 0.444 amperes. Therefore, the final answers are: the capacitive reactance is 636.6 ohms. The RMS current is 0.314 amperes. And the peak current is 0.444 amperes. About our next objective: impedance. It is the total opposition that a circuit offers to the flow of alternating current. It combines both resistance, due to resistors, and reactance, due to capacitors and inductors, meaning it represents everything that hinders the movement of electrons in an AC circuit. Mathematically, it is represented as impedance Z is equal to the square root of the sum of the resistance squared, and the difference between the inductive reactance and capacitive reactance squared, where Z is the impedance, I is the resistance. XL equals 2 times pi, times frequency times inductance, is the inductive reactance. XC equals 1 divided by 2 times pi, times frequency times capacitance, is the capacitive reactance. Let's solve this example. We are given a circuit with a resistor of 300 ohms and a capacitor of 8 microfarads, connected in series. The applied alternating voltage is 24 volts RMS, at a frequency of 60 Hz. Find 1. The reactance of the capacitor. 2. The current flowing in the circuit. 3. The voltage across the capacitor. B. If the capacitor is replaced with an inductor of 120 mH, calculate the impedance of the new circuit and the voltage across the inductor. Solution. We are given the resistor is 300 ohms. The capacitor is 8 microfarads, which equals 8 times 10 to the power of minus 6 farads. The frequency is 60 Hz. The root mean square voltage is 24 volts. Part 1. Finding the capacitive reactance. The formula is reactance of a capacitor equals 1 divided by 2 times pi times frequency times capacitance. So, 1 divided by 2 times pi times 60 times 8 times 10 raised to the power of minus 6. When calculated, this gives approximately 332 ohms. Part 2. Finding the current in the circuit. The impedance of a series resistor capacitor circuit is equal to the square root of the sum of the resistor squared and the reactance squared. That is, the square root of 300 squared plus 332 squared. This equals about 447 ohms. Now, current equals voltage divided by impedance. That is 24 divided by 447, which gives approximately 53.7 milliamps. Part 3. Voltage across the capacitor. The voltage across the capacitor equals current multiplied by capacitive reactance. That is 0.0537 multiplied by 332, which is about 17.8 volts. Part B. If the capacitor is replaced with an inductor. The inductor is given as 120 mH. The resistor, R, is 300 ohms. The frequency, F, is 60 Hz. The root mean square voltage is 24 volts. The reactance of an inductor is equal to 2 times pi, times frequency times inductance. That is 2 times pi times 60, times 0.12, which is approximately 45.2 ohms. The impedance is then the square root of 300 squared plus 45.2 squared. This is about 303 ohms. Now, the current is voltage divided by impedance. 24 divided by 303, which gives about 79 milliamps. Finally, the voltage across the inductor is equal to current multiplied by inductive reactance. That is 0.079 multiplied by 45.2, which is approximately 3.6 volts. Here are the answers. Option A. The capacitive reactance is approximately 332 ohms. The current is approximately 53.7 milliamperes. The voltage across the capacitor is approximately 17.8 volts. Option B. The impedance is approximately 303.4 ohms. The voltage across the inductor is approximately 3.58 volts. You've completed this lesson, well done. Let's test your memory with a few quick questions, a fun way to check what you've learned. We covered capacitive reactance and then discussed impedance. I trust you found the lesson both interesting and informative. In our next class, we'll continue with simple AC circuits, part 3. Thank you.